Chapter 2, Part 1, Basic Chemistry. In order to begin with, let's first define what is matter. Matter is, quote-unquote, the stuff of the universe. So this is anything that has mass and takes up space. We see matter occurring in three main states. The first state of matter is a solid. A solid has a definite shape and volume, and the examples of solids that you might find in the body would be things like the bones. The other state of matter is liquid. Now, liquid has a definite volume, but a changeable shape. Okay. For example, the blood. You could imagine that you could have the same volume of liquid and move it from one container to another. In this, the shape would change, but the volume would stay the same. Finally, we have gas. A gas is both a changeable shape and volume. Think about a balloon that is full of air or helium. Right? In a hot car, that balloon would expand, and in a very cold room, that balloon might contract. We haven't changed the number of molecules of gas, but rather we've changed both the shape and the volume. The second part of chemistry is energy. Energy, by definition, is the capacity to do work, which means to put matter into motion. In this, we're going to look at two different types of energy. The first is kinetic energy, and that is energy of action. Okay? So when you have something that is moving, right, it is said to have kinetic energy. There's also potential energy, and this is energy of position, which is a stored or inactive form of energy. Now, the best way to think about the way we can move from one type of energy to the other, kinetic to potential, is to think about tossing a baseball up in the air. As that baseball is traveling up through the air, it has kinetic energy, energy of movement. At the very top of its arc, there is a moment where the movement shifts from upward to downward, and at that moment, that baseball has maximal potential energy and minimal kinetic energy because it's not moving. So we can see this movement and change in kinetic to potential energy. Now, in terms of energy, there's also different forms of energy, and those different forms of energy are going to be where and how we store and utilize energy. The one that we will focus on in anatomy and in physiology, especially when we look at digestion, is chemical energy. Okay? This is energy that's stored in the bonds of chemical substances. Another type is electrical. Now, when you hear electrical, you might think about the electricity that we use in our homes. Electrical energy, though, is the movement of charged particles. We will see that in the human body, electrical energy will come in the movement of charged particles known as ions, which we'll cover later in this lecture. There's also then mechanical energy, and mechanical energy is directly involved in moving matter. Examples of mechanical energy that we will talk about in terms of anatomy and physiology will be the movement of muscles pulling on bones. The last of these forms of energy we will call radiant or electromagnetic energy. This is energy that travels in waves. So this would be things like our visible light, ultraviolet light, and X-rays. Now, these different forms of energy can easily be converted from one form to another. Okay? When this occurs, there is always some amount of energy that is lost as heat. Okay? If you want to think of an example, think about the example of your moving vehicle. You take gasoline, which is a stored form of chemical energy, put it into your car. That is then converted from that chemical energy. It is ignited within the pistons. Those pistons then move, being transferred into mechanical energy. That mechanical energy in turn eventually turns the wheels. Now, if you've driven your car for any period of time, heat is released as a byproduct of that. Now, we're not going to spend a ton of time looking at energy, so I want to bring things back to looking at matter. Right? We're now going to more clearly define what matter is made of. So in terms of the composition of matter, there are a few key terms that we have to define. This diagram here shows us the periodic table of the elements. Elements are, by definition, unique substances that cannot be broken down by ordinary chemical means. These are going to be made of more or less identical building blocks for each element, which we will call atoms. Each element then has a unique atomic symbol, a 1 or 2 letter chemical shorthand for each element. So for example, over here we see the letter C. This letter C is for carbon. Okay. Over here we have N. N is for nitrogen. Okay. Carbon and nitrogen are 2 distinct elements, and we're going to talk about these because they're actually extremely important in biological systems. Carbon and nitrogen are 2 of the 4 major elements of the human body. The other 2 major elements are oxygen and hydrogen. These 4 together comprise more than 96% of the approximate mass of the human body. Some of the different places that we see these are going to be in our organic compounds, which we will discuss later on. In addition to these major elements, which you must know both the name of and the symbol for, as well as some examples, we also have what are called lesser and trace elements. These lesser and trace elements are also important, but they are in a much smaller overall proportion of our mass. Some of the important ones will be calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. In this class, we will definitely talk quite a bit about chlorine. We will definitely talk about sodium. Okay. In fact, as we look at examples, this sodium and chlorine will be very important when we talk about what are called ionic bonds. We also then have trace elements. These trace elements occur in very small amounts. One example would be fluorine. Fluorine is actually required for the development of strong teeth. These are usually required for the activation of enzymes. Now, all of these differences that we see in elements all actually have the same basic structure. All atoms are composed of 3 main subatomic particles. Okay? We have the proton, which we usually depict as being a plus. Okay? Protons have a positive charge, and they have a mass of 1 atomic mass unit, or AMU. Neutrons then are neutral, or have no charge, and they also do have a mass of 1 AMU. Electrons have a negative charge, and while they have a mass, it is so small in comparison to those of protons or neutrons, we consider it to be near to 0 atomic mass units. The way that atoms are organized, we have different models to understand this. And in this course, we will use this planetary model in which the nucleus is made of the protons and neutrons at the center, then surrounding and moving around in an orbital fashion, like the planets revolve around the sun, we have the electrons. Now, this isn't exactly the most correct way. These electrons actually move around in a more of a cloud formation, but that's really hard in terms of drawing it on the board or thinking about it. So we'll simplify it to this planetary model to understand. Now, there are certain rules in terms of atomic structure, and the first of those rules is that the number of protons is what's going to dictate the element. So here we see 3 different elements, and what varies and that changes is the number of protons. So here we have 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium. These also do have different numbers of neutrons and electrons, but as we will see later on, differing numbers of neutrons and differing numbers of electrons within an element form ions and isotopes. As we try to identify elements, we have what's called the atomic number, and that is equal to the number of protons. As I said, that first rule is that the number of protons defines the element. The second number that we see is the mass number, and the mass number is equal to the number of protons and neutrons. So for this example C, which hopefully you recognize as being carbon, carbon has an atomic number of 6 and a mass number of 12. That means carbon has 6 protons. Carbon then also has 6 neutrons. Okay? The mass number of 12 minus the number of protons gives us 6 neutrons. And we can see that represented here, where we have 1, 2, 3, 4, 5, 6 protons and 1, 2, 3, 4, 5, 6 neutrons. Now you may have also heard of the atomic weight. The atomic weight is going to be the average of all of the different possible isotopes. So in order to understand the atomic weight, we have to define what are isotopes. Isotopes are different versions of the same element that have the same number of protons but different numbers of neutrons. So here we have what is called carbon-12, where we have 6 protons and 6 neutrons, giving us a mass number of 12. Here we have carbon-14. We still have 6 protons because that defines carbon, but here we have 14 as the mass number, so we will have 8 neutrons. And we can see that here, 1, 2, 3, 4, 5, 6, 7, 8. The atomic weight then would be the average of all of the carbon-12s and the carbon-14s. We can see this example with isotopes of hydrogen. Hydrogen has 1 proton, 0 neutrons, and 1 electron. If we add or change the number of neutrons, we change this to deuterium, right, which has 1 neutron, or tritium, which has 2 neutrons. These are all isotopes of hydrogen. Now you may have heard of isotopes having to do with radioactivity. There are some what are called radioisotopes, and these are atoms that undergo a spontaneous decay called radioactivity. This is when certain parts of that element are given up, and that element may either change either the type of element that it is in the case of alpha decay, or it may change its energy level in the case of both beta and gamma decay. Now in terms of looking at molecules and compounds, we're going to take elements and put them together in a certain way to create molecules. Now we can have a molecule of an element, and here we are taking 2 of the same atoms and are holding them together by chemical bonds. For example, if we have 2 oxygen atoms, those will form O2 gas. We also then have molecules of a compound. Here we have different kinds of atoms or different elements that are being chemically bonded together. The example would be water, in which we have 2 hydrogen atoms and 1 oxygen atom bound together. And we will see examples of both of these. When we discuss bonding or chemical bonding, the way chemical bonding is going to occur is it's going to occur between different atoms using the outermost shell of electrons. These electron shells that surround the nucleus are where our bonds will form. And we will see that the valence shell, which is the outermost level, is where we have our chemically active electrons. These electrons will behave in a manner so as to achieve a type of stability dictated by what's called the octet rule. Oct meaning 8. What this rule states is that with the exception of the very first shell, which fills with only 2 electrons, the valence shells of electrons will strive to achieve 8 electrons to have stability. So let's see some examples of this. Here we have 2 examples of chemically inert elements. These are elements that will not react. One example would be helium. Okay. Helium has 2 electrons in its shell, and this is the outermost shell that helium has. So helium does not react. It is inert. This is an example of neon. Neon has 2 electrons in its inner shell and 1, 2, 3, 4, 5, 6, 7, 8 in its outer shell. Having 8 valence electrons gives this neon stability, and therefore it is also inert. So what we will be looking at when we look at chemically reactive elements are elements that do not have a full valence shell. In terms of the first shell, only hydrogen is reactive, having only one electron in its outermost shell, which is the first shell. Here we have carbon. Previously we saw that carbon had 6 protons. If there is no charge involved, then it must have 6 electrons. So here we see 1, 2 in the first shell, 1, 2, 3, 4 in the second shell. Oxygen has 6 electrons in its valence shell, and sodium has 1 electron in its valence shell. So all of these will react in a way as to try and achieve 8 in their outer shell, with the exception of hydrogen, which will try to either achieve 2 or, interestingly enough, 0. Now the different types of bonds that we are going to see are going to be dictated by how these elements behave when they react. The main types of chemical bonds we will discuss are ionic bonds, covalent bonds, and then a third type called hydrogen bonds, which are actually bonds usually between molecules or between distant parts of molecules. We will begin looking at ionic bonds. The definition of an ion is a charged atom. What occurs is that either an electron is gained or lost. If you have the gain of an electron, you are gaining negativity. So we have what is called an anion, or a negative ion. If an electron is lost, we have an overall positive charge, and these are called cations. Now let's take a look at how this can occur. Here we have sodium. Sodium has 11 protons and 11 electrons, so it does not have a charge. Because it has 11 electrons, we can see 1, 2 electrons in the first shell, then 3, 4, 5, 6, 7, 8, 9, 10 in the second shell, leaving 1 lone electron in its outermost shell. Now for sodium to achieve an outer shell that has a full 8, it could gain 7, but that would be quite difficult. So instead, sodium is going to look to lose or give up this electron. On the other side of things, we see the chlorine atom here. Chlorine has 17 protons and 17 electrons. We can see that in its outermost shell, then, it would have 7 electrons, so it is looking to gain an electron. So the formation of ions occurs when this sodium gives up an electron, and that electron moves over to chlorine. Now we have a sodium ion that has an inherent positive charge because there's now 1 more proton than there is electrons. And we have a chloride ion that now has a negative charge because it has 1 more electron than it has protons. The actual ionic bond occurs because this positive ion is attracted to this negative ion. This example of what we now call sodium chloride is quite an interesting example and will be very important as we go through and talk about biology. Now the interesting part is that when we have a sodium ion and a chloride ion, these are 3-dimensional, even though they are represented 2-dimensional in this presentation. So what that means is ionic compounds often form crystals. So here we have our negative chloride ion, and it would be surrounded by positive sodium. Likewise, this positive sodium would be surrounded by negative chloride, so on and so forth, forming a crystalline structure. Now please understand that this transfer of electrons from sodium to chloride is not a transient change. It does not go back and forth. When this change occurs, we completely change the properties of the elements. So just as an example of that, sodium in its elemental form is a gray metal that you can cut with a knife, and if you throw it in water, it is explosive. Chlorine is a gas that if you inhale it, it is deadly. When these two change and sodium becomes a sodium ion, giving up an electron to make the chloride ion, we form an ionic substance called sodium chloride, or better known as table salt. That concludes our overview of ionic bonds. So let's now move to covalent bonds. In covalent bonds, we have bonds formed by the sharing of two or more electrons. Notice the name covalent, meaning sharing of valence electrons. This occurs when we have molecules that cannot easily give up an electron. The example shown here shows a carbon atom which has 4 valence electrons. Hence, this carbon atom needs to get 4 more electrons to reach its stable 8. What this carbon atom can do is it can bond with 4 individual hydrogens, each hydrogen needing 1 electron to reach its stable state, creating a molecule of methane gas. Here we see that the 2 electrons are being shared. Carbon, therefore, thinks that it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. This covalent bond is an actual sharing of those electrons. We can see this occurring in a double manner. So an atom of oxygen and an atom of oxygen will form a double bond in which each seeks to have 2 additional electrons. So there is a sharing of 2 separate pairs. And this is how we see the formation of a molecule of oxygen gas. In a few rare instances, we may see a triple bond. This is nitrogen gas, in which we have a single nitrogen atom and a single nitrogen atom forming 1, 2, 3 covalent bonds. Because these are shared, sharing is not always equal. When you have electrons that are shared equally between atoms, that will produce a nonpolar molecule. However, if there is unequal sharing of electrons, you'll have polar molecules. A polar molecule occurs when you have some degree of relative positivity or negativity within a molecule. When we have atoms that have 6 or 7 valence shell electrons that are taking part in a covalent bond, we say that these are electronegative and that they are attracting the electrons. Whereas atoms that have only 1 or 2 valence shell electrons are electropositive in that they lose the electrons. Now, they're not losing them entirely, but they're losing their tight hold on them. What that leads to is a molecule like water over here, where even though there are covalent bonds, this oxygen, which is highly electronegative, can pull on the electrons and pull them closer. So the oxygen portion is more negative and the hydrogen portions are more positive. So here we have a nice overview of the difference between an ionic bond, where we have an actual exchange of electrons leading to a fully positive and a fully negative part, a polar covalent bond, and a nonpolar covalent bond. All of these bonds, though, occur and create molecules. There are also something separate called hydrogen bonds, and hydrogen bonds is a force of attractions between either 2 different molecules or different regions of the same molecule. These are too weak to actually bind together atoms. However, these are very common in dipoles such as water, so that's what's shown here. And what you see occurring is that you have the slightly positive hydrogen being attracted to the slightly negative oxygen. This is going to be responsible for some of the important qualities that water has, including surface tension. This is a very important intramolecular bond as well in things like proteins and DNA, and it gives a molecule its 3-dimensional shape. Now, these bonds become important in terms of chemical reactions, and as we discuss physiology, physiology really comes down to chemical reactions. What a chemical reaction is when a bond is either broken, formed, or rearranged. The simplest way to think about chemical reactions is you have something that is going to react, called the reactant, to produce something called the product. We always have some amount of balance, so whatever goes into the reaction has to come out. So here we have an H plus an H yielding H2. Here we have 4 H's plus a C yielding CH4. When we have a subscript number here in a molecule, it means that we have 4 atoms of hydrogen bound to a carbon, creating a single molecule, in this case called methane. Now, there are different ways that these chemical reactions can occur. We can have a combination in which 2 separate reactants form a new third product. We can have a decomposition in which 2 new products, A and B, are formed from an initial reactant that is broken. Or we can have an exchange. And really an exchange is a combination of a combination and a decomposition reaction occurring at the same time. Now, everything we've discussed has to do with these chemical reactions occurring. Chemical reactions occur, and there are different things that can influence the rate of chemical reactions. This can be influenced by temperature. So if we have a higher temperature, temperature is actually a measure of the movement of molecules. So what you can imagine is, as we have a higher temperature, the molecules are moving more rapidly. As they move more rapidly, there's more chance that they would bounce into one another or bang into one another, leading to chemical reactions. The particle size is also important in influencing the rate of chemical reactions. So when you have smaller particles, they can move faster and therefore increase the speed of the chemical reaction. The other thing that is important is the concentration. So if you have higher amounts of the particle, more of the particle floating around, there's more chances that they'll bump into one another, creating a faster reaction. And then there are catalysts. Now, catalysts are very important. Catalysts will increase the rate of the action without being chemically changed themselves. In biology, in biological systems, we use the term enzymes to describe biological catalysts, and this will be an extremely important term as we go through physiology. Now, up until this point, we have looked at molecules where we have things bound together. I want to briefly go through mixtures. Now, in mixtures, which are quite common in the human body, we have 2 or more components that are physically intermixed but not chemically bonded, which means though it might be difficult to do so, these things can be separated out. We classify these as either solutions, which are homogeneous or equal mixtures of components, colloids or emulsions, which are heterogeneous or unequal mixtures, and the solutes do not settle out, or suspensions. These are heterogeneous or different, where the visible solutes tend to settle out. The main difference between mixtures compared to compounds: there's no chemical bonding that takes place in mixtures, so they can be separated out by physical means.